All right, welcome back, everyone. Today we're going to be talking about Chapter 6, the normal distribution and other continuous distributions. Okay, so the objectives for this chapter is to compute probabilities from the normal distribution, how to use the normal distribution to solve business problems, to use the normal probability plot to determine whether a set of data is approximately normally distributed, and finally to compute probabilities from the uniform distribution. Okay, so what is the continuous probability distribution? Remember, we talked about this, about how we can have a counting process and a measuring process, right? So probability distribution is a counting process. And basically, a continuous variable is a variable that can assume any value on a continuum, basically that can assume unaccountable numbers of values. For example, you're trying to measure how thick an iron is, the time that you will need to complete a task, the temperature of a solution, height in inches. These probabilities can take any value depending only on the ability to precisely and accurately measure. So, for example, imagine that you are cooking a steak, and let's say that maybe you like your steak medium well or rare, or or well done. It depends, right, on your taste. So you do have an analog thermometer, and you stick your thermometer into the steak. You find out the temperature is 137 degrees. But then you say, well, I like my steak medium well, so it should be at 140 degrees. And so you go and grab a digital thermometer, and now you can more precisely measure the temperature, and you realize it's 137.9. And then you realize you have an even better thermometer, and the temperature is 137.59. Anyway, the more precisely the instrument you have, the more precisely you can tell what the temperature is. And that value could continue up to infinity. So you cannot really precisely measure how exactly the temperature is, because unless you have a device that could measure any temperature to infinity, which does not exist, you could not precisely describe the temperature of that item. So when you say 137.52 is an approximate temperature. So the probability distribution, they're going to have different shapes depending on what type of distribution it is. So we have here the normal distribution, the one on the left. That's the one that we're going to be assuming, working on the most. And this distribution is symmetrical. As you guys can see, it's bell-shaped. And the values are going to go from negative infinity to positive infinity. We do have the uniform distribution, which is also symmetrical and is known as the rectangular distribution because of its shape. And every value between the smallest and the largest is equally likely. So you are equally likely to get any value from the smallest to the largest. For example, you are rolling a dice. So you're equally likely to get a 1 as you are equally likely to get a 6. And then we have the exponential distribution. This only has positive values, so you start with the 0. And as you guys can see, it's right skew, so the data is skewed to the right. That means the mean is higher than the median, and the values are going to go from 0 to positive infinity. All right, let's talk a little bit more about the normal distribution, because again, this is the one that we're going to be using the most. And in real life, that's where most of the data comes from. Again, as you guys can see, the normal distribution is bell-shaped. It is symmetrical. That means all the values to the right of the mean are going to equals to all the values to the left of the mean. One thing that is interesting about this distribution is the mean, the median, and the mode are equal. So remember how we discussed those central tendencies a few chapters ago? So you have your mean, you have your median, and your mode. When it comes to the normal distribution, all of those have the same value. The location is going to be determined by the mean, which is a mu, the letter Greek represented by the letter Greek mu, and the spread is determined by the standard deviation. So the random variable has an infinite theoretical range from negative infinity to positive infinity. So changing the mu or the mean shift the distribution to the left or to the right, and changing the standard deviation is going to increase or decrease the spread, because we already know that the standard deviation is actually measuring the spread. On this example, you can see that A and B have the same mean, right? So you guys see the mean is the same, but the standard deviations are different. So on the case of A, the standard deviations is larger because the data is more spread. In the case of B, the standard deviation is smaller. As you guys can see, is more contracted, so there is less spread on B. Now, B and C, they have different means. That is pretty obviously, because that is this line right over here, right? That's where your mean is. So they have different means, but also the standard deviations are different. You can see this one is the peak is higher, so that means the standard deviation is smaller. This one has more spread. Now I think A and C, they have about the same standard deviation. They do have different means, but the standard deviation is about the same. Here is a formula for the normal probability. You don't need to memorize this. It's just kind of like for your information only. I know this could look like a very powerful formula, but like everything else in statistics, once you break it down, it's not that difficult. Anyway, you don't need to memorize this. Excel in Minitab will do most of the calculations for us, so you don't really need to memorize this formula. But it's a good idea to figure out, familiarize with this and know what it means. All right, let's talk about the standardized normal. What is the standardized normal? Basically, any normal distribution, right, with any mean and standard deviation combination can be transformed into the standardized normal distribution, Z. To compute the normal probabilities, you need to transform X units into C units. So the standardized normal distribution, C, has a mean of 0 and a standard deviation of 1. So remember, the mean, the center, is going to be 0, and any standard deviation is going to be 1. And this is the formula to transform any X into the standardized normal, right? So when we talk about X, could be whatever measure you are using. So let's say you're using miles, or you're using Fahrenheit, or any other type of measuring. So how you will need to translate that into standardized. So the way you do it is your C is going to equal X, which is your value, minus the mean, and you divide that by the standard deviation. Because remember, the C distribution always has a mean of 0 and a standard deviation of 1. So here is the standardized normal distribution, which is also known as the C distribution. Your mean is going to be 0. So here is 0, and every standard deviation is going to have a value of 1. So any value above the mean has positive values. So anything to the right or above the mean is positive. Anything below the mean or to the left of the mean is going to have negative values, because as we talked about, this is symmetrical. So when you talk about here 1, this is 1 standard deviation. If you were going to be here at the left, that'd be a -1 standard deviations. Here is the formula for the standardized normal probability. Again, you don't really need to memorize this, but it's a good idea to be familiar with it. So let's take a look at an example, right? So if X is distributed normally, which mean of 100 and the standard deviation is 50, the Z value of X equals 200 is. So here is, remember the formula, how we translate these X values into Z values, right? So you got the value that you have, the 200, minus your mean, which is $100, and then you divide that by the standard deviation, which is 50. So your Z value, in this case, will be 2.0. And basically what this is saying that X equals 200 is 2 standard deviations, or 2 increments of 50 units above the mean of 100. So comparing X units and C units. So on this table here, from the data that we have, we know that the mean is 100, which know that on the C table, the mean is always going to be 0. So, and then we already did the formula. We translated those 200 into C units, right? And so in this case, it's 2.0. So you note that the shape of the distribution is the same, only the scale has changed. So we can express the problem in original units, x, or you can use the standardized units, which is the z table. So finding the normal probabilities. The probability is measured by the area under the curve. So here we're trying to find the probability of the yellow area, right? So what is the probability that A is equal or less to X and X is equal or less than B? One thing that you need to keep in mind is that the probability of any individual value finding the probability of any individual value is 0. And the reason is because those values, they have no area under the curve. The reason is because you cannot find any specific value to infinity. So like we were trying to find what is the exact temperature of the steak that we were trying to cook. First we say, well, it's 137.5, 137.52, and we could continue all the way to infinity. So because of that continues all the way to infinity, we have no area under the curve. So it's, the probability of finding a specific value will be 0. The total area under the curve is 1.0, so any value from negative infinity to positive infinity will equal 1. So basically all this area here under this curve equals to 1. So because remember, this is symmetrical, anything to the left will equal 0.5, anything to the right will equals 0.5. The cumulative standard normal table in the textbooks gives the probability less than a desired value of z. So from negative infinity to z. So if you look at your table, right, and you're trying to find the probability of z being less than 2 standard deviations, that will be 0.9772. So when you look at the z table, you're looking anything to the left of the value that you are trying to find out. So in this case, 2 standard deviations, you are looking anything below here, and that's 0.9772. Basically, the probability of finding something higher than 2 standard deviations will equals 0.1 minus 0.9772. When you look at the standard this Z table, you can see the values here. The first one will show the first decimal point, and then the columns give you the values of the second decimal point. So let's take a look at the Z table here to familiarize ourselves with it. Okay. So here is our Z table, and here is our 0. Here is our 2.0 value right over here. So 2.00, right? That will be 0.9772. If you want to find out 2.01, then you will have 0.9778. So again, this one, the first part gives you the first decimal point. The second one gives you the second point, the second part of the decimal points. All right, let's go back to our PowerPoint here, and okay, so let's say we find the probability that A is less than X and X is less than B when X is distributed normally. So we can draw the normal curve for the problem in terms of X. So we can say that first thing we need to do is we need to draw the normal curve on the problems in terms of X. So it's always a good idea. Every time you're doing these problems, just draw the curve, make the draw, so that way you can visually see what you're trying to find out. Once you're doing that, you need to translate the X values into the Z values. And then finally, you need to use the standardized normal table, the one that we just looked at it, to find those values. So let's take a look at an example here. In this case, let X represent the time it takes in seconds to download an image file from the internet. So suppose that x is normal with a mean of 18.0 seconds and a standard deviation of 5.0 seconds. You need to find the probability that x is less than 18.6. So again, on this case, you're trying to find out how long it takes to download image from the internet. We know it takes about 18 seconds, which is a long time. This gotta be really old. It shouldn't take that long to download image from the internet. So anyway, we have 18.0, standard deviation is 5.0, and we're trying to find the probability that is going to happen in less than 18.6 seconds. So first thing, we do our drawing, right? We find our mean, 18.0, we're trying to find 18.6, and then we highlight that in red so we know which area we're trying to look at it. Second, we need to make those x values into c values. So the way we do that is we got our value that we're trying to find out, which is 18.6. We subtract 18.0, and then we divide by the standard deviation, which in this case is 5.0, and that'll give us 0.12. So here on the left, we do have our x values, 18 and 5. Here on the right, we have our standardized values, which our mean is 0. In this case, we already find out that our c value is 0.12, which equals to 18.6. Okay, so what we do now, we go to the C table, and on C table we find out that 0.1 and at 0.2 is 0.5478. So let's go back to our table here so we can look at it. Okay, here it is. So here is 0.1 and 2. So you guys can see here is 0.5478. So 0.1, right? 0.478. Okay. And this is, we have a screenshot here. So basically we're saying is the probability that x is less than 18.6 is the same as saying the probability of c is less than 0.12, and using the table we find out that is 0.5478. Okay, now we are trying to find out the probability that x is higher than 18.6. So what it's saying, what is the probability that it's going to take us longer to download this image from the internet than 18.6 seconds? So again, we draw our table here, and we're saying we need to find the red area, right? The area to the right of 18.6. Now, we already did some of this work on our prior example. So we already know that 18.6 equals c on the C table is going to equal 0.12 standard deviations. And remember what we learned, that the entire area under the bell curve is going to equal 1.0. And we already find out on the prior example that the area to the left of 0.12 is 0.5478. That's something we find out earlier, right? So in this case, what we're going to do is subtract 1 minus 0.5478, and that'll give us the area to the right, which equals 0.4522. Okay, on this example, it's a little bit different. What we're trying to find out is the area between 18.0 and 18.6. So suppose x is normal distributed with a mean of 18.0 and a standard deviation of 5.0. We need to find the probability that 18 is less than x and x is less than 18.6. So we need to calculate the c values, right? We already have the c. We know that the mean for c is going to equal 0. We know that already, so we really didn't need to do that. But you can just do it there. 18 minus 18 divided by 5 is going to equal 0. And then we did this earlier. 18.6 minus 18 divided by 5 equals 0.12. So we're trying to find the probability that 18 is less than x and x is less than 18.6, which is also saying that we need to find the probability of 0 being less than z and c being less than 0.12. So we need to find this area on the red. Again, the first thing you need to do is draw the bell curve. You need to figure out the 18 and 18.6. So you say, I'm trying to find this area here. So how you will do that? We already did that earlier, right? We find out that Z, if you look at the Z table, you know that the mean is zero zeros. So on this case, remember, the entire area is 1. So the area here at the 0 is going to equal 0.5. Let me go back here. Okay, so we already know that the area to the left of the mean is 0.5. We learned that earlier. So that is, we already know that. And we also, on a prior example, we saw that the area of 0.12 standard deviations of C is going to equal 0.5478. So we already know that this is going to 5 minus 4.78, that's give us 0.5478. Okay, so now we need to come on. Okay, so we need to find the probability now. Hold on, let's go back in here. What we're talking about here. So this is where we get the 0.478, right? So we know the area to the left is 0.500. The area to the right is also 0.500. Because we had already found 54.78, all we have to do is subtract the 0.500 from 54.78, and that's how we know the area between 0.0 and 0.12 is 0.0478. So our probability that we are going to get download a file is going to take between 18 and 18.6 seconds, is going 0.0478. Okay, so on this one, it's kind of the same thing. What we're trying to do is find the area between 17.4 and 18.0. So this one is going to be to the left. And we'll do the same thing. First we do the drawing. Then we translate the p values into the x values into c values. So again, the only thing that is different now, instead of having a positive 0.2 standard deviation, we have a negative 0.12 standard deviation. That means it's to the left, and it will be very, very simple. So the probability will be exactly the same. Remember, these are symmetricals, so you have anything below the mean, which is 18, will be 0.5. So we gotta do is subtract the value that we had already found earlier, the 0.522, and it'll give us the same value, 0.478. The normal distribution is symmetrical, so this probability is the same as the one that we found out earlier. Let's talk about this empirical rule. This is a really good idea to keep that in mind and memorize if you need to. What can we say about the distribution of values around the mean for any normal distribution? Basically, we're saying here, we have our mean, which, remember, for the standardized table, the C table is always going to equal 0. And so the mean minus 1 standard deviations and the mean plus 1 standard deviations, all of your values, 68.26 of the values, are going to be between those two standard deviations, negative 1 standard deviations and 1 standard deviations above the mean, and 68.26% of your values are going to be found in there. Also, if you go as far as 2 standard deviations, 95.44% of your values are going to be between 2 standard deviations below the mean and above the mean. If you go as high as 3 standard deviations, then you can capture 99.73 of all of your values. So any value higher than 3 standard deviations is an extreme value and something that you can say this is something that is not normally occurring, does not happens very often. So anything about 3 standard deviations is something that you might want to consider an outlier. Here we need to do is here are the steps to find the x value of a known probability. So we're trying to find the z-value of the known probability. What we need to do is then, after we find the z-value of a known probability, we need to convert those x units using the formula. So remember the formula that we have to convert x to z. Now we need to kind of revert the same formula to find x values, and that's going to equal the mean plus the z values times the standard deviation. Here is an example. So let's x represent the time it takes in seconds to download an image from the internet, and we know that x is normal distributed with a mean of 18 and the standard deviation of 5.0. So we need to find x values such that 20% of download times are less than x. First thing we do, we always draw our figures so we know what we're dealing with. Basically, in this case, we're trying to find out this 0.20 below the from the curve. So find the z values for the known probability, and then what we're going to use the standardized normal probability table, and then 20% area in the lower tail is consistent with the z value of 0.84. So here it is, you have 0.08, here's 0.84, and this is as close as we get. We don't get exactly 0.2000, but the closest one that we can find is 0.2005. So after we do that, all we have to do is convert the x units using the formula that we have, right? X is going to equal mu plus, or the mean, plus z times the standard deviation, so 18 plus, and then you have negative 0.84 times 5, and once you do that, you have 13.8. So 20% of the values from a distribution with a mean of 18.0 and a standard deviation of 5.0 are going to be less than 13.80. Now, one thing that we know is not all continuous distributions are normal, right? So it is important to evaluate how well the data set is approximated by a normal distributions. Normally distributed data should approximate the theoretical normal distribution, right? That means the normal distribution is bell-shaped. So remember the bell shape that we've been talking about, that is symmetrical, where the mean is equal to the median. Remember we talked about those empirical rules, so 68.4% of the values are going to be between 1 standard deviations, 97.72 of the values are going to be 3 standard deviations. So that's something that we need to remember, right, when trying to evaluate how normally distributed this data is. One thing that is known, that is new, we haven't talked about, is the interquartile range of a normal distribution is 1.33 standard deviation. So if you're trying to measure the inner quartile, you should be between 1.33 standard deviations. Comparing data characteristics to theoretical properties. So you construct charts or graphs for a small or moderate-sized data sets, construct a stem and leaf display. Remember, we learned that earlier in chapter 2, I believe. So you have to construct a stem and leaf display or a box plot to check for symmetry. For large data set, does the histogram or polygon appears to be bell-shaped? And then do the mean, median, and mode have similar values? Always remember, on the normal distributed table, the mean, the median, the mode, they all have similar values. The values are the same. And the inner quartile range is 1.33 standard deviations, and the range has to be approximately 6 standard deviations, more or less. So you observe the distribution of the data set. You are supposed to expect 2/3 of the observations between 1 and -1 standard deviations. So 80% of the observations should lie between 1.28 standard deviations, and about 95% of the data should be between 2 standard deviations from the mean. Is the normal probability plot approximately linear, right? So that's another thing we need to find out if the data is a straight line with a positive slope. So what you do is you will arrange the data in an array, and then you find the corresponding standardized normal quantile values. You plot the pairs of points with observed data values of x and the vertical axis on the standard normal quantile values of z on the horizontal axis, and then you evaluate the plot for evidence of linearity. And you should get something like this, right? So the slope is positive, that means it's going up, and you should get something here, your x values from 9, and here your z values from negative to positive. So this is what a normally probability plot will look once you put it into an image. So here is something that is nonlinear, left skew. That's kind of what it looked like. The normal distribution right on the center, you guys can see, is upward trending, and then you have a right skew data on the one on the right picture. On the box plot, you guys can see here how the box plot will look. So on this one, we can see that the box plot appears a slightly left skew. And then, so you're trying to remember, you're looking for symmetry for the standard, for the normal distribution. Here you can see, right, the mean, the median, and the mode, they have to be the same. On this case, we can see that the median is a little bit higher than the mean, and the mode is higher than both the median and the mean. Also, here is the 5-number summary, right? So you have your minimum is negative 3.40, first quartile 6.14, the median is 8.09, the third quartile 9.86, and the maximum is 15.32. The mean is approximately the same as the median, not exactly the same, but it's somewhat closer, right? If I normally distribute, the means and median are equal. The box plot, as we saw, is a slightly left skew. The inner quartile range is 3.72, which is about 1-2-point standard deviations. The range is 18.72, is equal to 6.21 standard deviations. So on a normally distributed range is 6.0 standard deviation, so somewhat close. We have the 68.75 observations are within 1 standard deviations of the mean. That is close to what we expect on a normal distribution percentage of 68.26. 79.38 of the observations are between 1.28 standard deviations. We expect that to be 80%, so it's somewhat close. 94.58% of the observations are between 2 standard deviations of the mean. So in a normal distribution, this should be about 95.44, so again, very, very close. The skewness statistic is 0.33, and the kurtosis statistic is 0.42. Each of those statistics should equal to 0, so it is somewhat close to 0. And so after we plot it here, this is what it looks like, right? So it's upward trending. So plot is close to a straight line and shows the distribution is approximately normal. So it's not exactly normal, but it's somewhat normal. It's close to normal. Okay, let's talk about the uniform distribution now. What is the uniform distribution? Basically, it's a probability distribution that has equal probabilities for all possible outcomes of the random variable, also called a rectangular distribution. Like we talk about the dice, right? You roll the dice, and the probability that you get 1 or 6 is the same. So this will be a rectangular distribution. Here you have a continuous distribution. Here's your formula. Again, you don't need to memorize this, but it's a good idea to know what it means. So just keep that in mind. Here is the mean of a uniform distribution. You have the mean is going to equals a plus b divided by 2, and your standard deviation, you have b minus a squared. B minus a to the second power divided by 12, and then you get the square root of that, and that will give you your standard deviation. Here is an example, uniform probability distribution over the range where 2 is less or equal than x and x is less or equal than 6. So you have 1 divided by 6 minus 2 equals 0.25 for 2 being less than x and x being less than 6. And so your mean, a plus b, 2 plus 6, that equals a divided by 2, that equals 4. And then you have 6 minus 2, that will be 4. And then you 4 times 4, that equals 16 divided by 12. And then you take the square root of that, is going to equals 1.1547. Here you're using the uniform probability distribution to find the probability that 3 is less or equal than x and x is less than equal to 5. So the probability, you have basically your base times your height, and that'll give you 2.0 times 0.25 or equals 0.5. Okay, let's wrap things up. We discussed computing probabilities for the normal distribution, using the normal distribution to solve business problems, and using the normal probability to plot to determine whether a set of data is approximately normally distributed. So remember those rules that we just talked about, right? And then computing probabilities from the uniform distribution. All right, guys, that's all I have. Let me know if you have any questions or something. Reach out to me if you need help with anything. Other than that, have a good day.